10.8 talks about geometric probability. And the basis of this is our definition of probability, which is the likelihood of an event occurring, which you're going to see typically written as this here. Okay, they'll use a capital P, and then whatever word or sometimes they'll just use a singular letter of what event or that defines the event. So if we're talking about putting everybody's names in a hat, my name included, and I ask the probability of likelihood of my name being pulled out of the hat, we would write it as probability, okay, capital P for probability, and then this is the event, so my name getting pulled out of the hat. Sometimes, like if we're a lot of times you've dealt with cards. What's the probability of pulling an ace out of a deck of cards? What's the probability of pulling a 3 out of the deck of cards? So that object in the parentheses is the event that we're interested in. This is simple probability, and we can get into very complex procedures and processes, and maybe you've already done some of that stuff, like conditional probability, throughout this course. We may, depending on the time that we have, we may address some of that, but I'm just going to skim the surface of probability here. If you were to go on to take a stats class, generally the statistics itself is predicated off of probabilities. A lot of the analysis that we do in statistics is got a foundation in probability, the likelihood of something happening. But in its most simplest version, the probability of an event, the probability of an event is the number of favorable outcomes, generally called successes, divided by the number of possible outcomes, generally referred to as the sample space, all the things that could happen. We got some bullets here. It says favorable outcomes is the number of items in your sample space that are aligned with the desired event. When I talk about a sample space, I'm talking about all the things that could happen. So if I'm going to pull an ace out of a deck of cards, so let's write this real quick. Probability of an ace out of a deck of cards, well, the sample space is how many cards are in a deck. There are 52 cards in a deck, so that's all the possible things that could happen. There's 52 different cards that we pulled out. 4 of those cards are aces, so the 4 is the number of favorable outcomes. I'm looking for aces. That's those are aligned with the favorable outcomes, and the 52 is aligned with the number of possible outcomes. So second bullet here, number of possible outcomes is the number of total items regardless of their alignment with the event. The number of possible outcomes is often referred to as the sample space. Probability can be written as a fraction between 0 and 1, a decimal between 0 and 1, or a percentage between 0% and 100%. The further you get into probability statistics, this is typically how your probabilities are going to be written. Geometric probability, is the use of geometric models to solve certain types of probability problems. So we'll see a variety of those examples in this lesson. It says, in geometric probability, points on a segment or in a region of a plane represent outcomes. And the geometric probability of an event is a ratio that involves geometric measures such as length or area. So the first type of problem that we're going to see is dealing with probability and length. And typically these types of questions you see, a lot of times they use the word Q. I think it's spelled Q-U. Let me see. And really, that's just a fancy word for line. Okay, if you're waiting in line at McDonald's, you could be referred to as being in a queue. If you're waiting on, if you call a customer service, a lot of times they will, they'll take you based on when you call. If there are people, all their representatives are on the phone on the line with somebody else, they'll say your phone call will be answered in the order in which you entered the line. So if there's 3 people waiting in front of you, you're going to be the 4th one, so you're 4th in the queue. But when we talk about waiting in lines, this is the concept, this is the idea that we're dealing with. It's dealing with the lengths, okay? So it says point S on segment AD is chosen at random, okay? So there's some point here on S that we're going to choose, and it's going to be random, okay? It might be anywhere on here, okay? They're going to say the probability that S is on BC, so the probability that S shows up right there on BC is the ratio of the length of BC, the ratio of that length compared to the length of the segment AD anywhere that point S could have shown up, okay? So if we take that small length right there and compare it to the entire length, that will give us the probability that a random point chosen will fall on BC. The way I like to think about a lot of geometric probabilities is if you had this line in front of you, okay? If it was drawn on the whiteboard or I don't know, on the grass out in front of you, whatever, maybe just a segment of that length, and I told you you're going to throw a dart at that line, and I'm telling you, you have to hit the line, because if we could hit anywhere else, that creates a completely different geometric probability question. But if I tell you that your dart has to hit this line, it has to hit it somewhere here, and I ask you, well, what's the probability if it has to hit? What's the probability that it falls on BC? Well, that would be the length of BC compared to the length of AD. Okay. So the examples that you see here, it says point K on ST is chosen at random. Okay. So point K is going to be somewhere on that segment. Okay. What is the probability that K lies on segment QR? So what's the probability that it lies right there? Okay. So the way I'm going to write this is, what is the probability that point K lies on QR? Okay. So what we're going to look for is the length of QR, okay, because that's where those are our favorable outcomes. That's what we want it to happen. So the length of QR, you can use your your ruler postulate here. I'm going to take 8 minus 5. That gives me 3. And if I'm looking at then ST, okay, remember, and maybe I should write it this way first. K on QR would be QR's length divided by the total number of possible outcomes, the sample space, which is ST's length. So like I said, QR's length was 3. ST's length is 12. So there's a 1 out of 4 or a 0.25 or a 25% chance that I randomly pick a point and that point comes from Q to R. Or, give you the visual. If you were standing here and this was that line segment was drawn on the whiteboard or a smart board in front of you, and you had to throw a dart with a suction cup on it, and I told you have to, when you close your eyes and you throw it, and I said, before you open your eyes, I say, your dart hit on the segment ST. It hit somewhere on ST. What's the probability that it landed on QR? it's this 0.25. That's the concept that we're getting at here. Okay. When they ask you this question here, what is then the probability that Q does not lie on QR? Okay. Well, a couple ways you can do that. You can say, okay, well, if it's not going to lie on QR, then it's got to lie either there from S to Q, or it's got to lie there from R to T. So the probability of K not on QR, there's a couple different ways you can write that. You can write it this way. Probability K, we use that kind of like squiggly tilde for not, and then on QR. But the way we do that is, okay, not on QR, so favorable outcomes would be either there, okay, so that's a distance of 3, or here, which is a distance of 6. Okay, so it could happen either of those places, so that's 9 out of 12 total. Divide gives me 3/4. That gives me 0.75 or 75%. Okay, so a common way of doing this is we talk about things called complements, and I think maybe so this concept right here, this concept is often referred to as the complement of an event. In particular, we found that PK lies on, or probability that K lies on QR, then the probability of, and we put this prime notation here, and I'm going to actually adjust that here in a moment on where we put that prime notation. It says P prime, K lies on QR, is how we would often write the complement of the event. Another method would be to rewrite the entire event as probability of K does not lie on QR. However, in probability statistics, it is often denoted with the complement symbol instead of that they use, and they use that. It's an apostrophe, but it's a prime notation. And I've got it written here, okay? The probability of an event, and when I have that apostrophe, it's the complement. So let's go back to just something real simple here. If I say the probability of picking let's say a number from a deck of cards, okay? So when I pick out my deck of cards, okay, 52 cards, and I'm going to pick out a number. Well, let's think about this. We've got, with cards, you've got your hearts, you've got your diamonds, you've got your spades, and you've got your clubs, okay? So hearts go from ace, and then they start ace is the one. And then they go 2, 3, 4, 5, 6, 7, 8, 9. And then you've got your jack, your queen, and your king. So each of these has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm missing something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm sorry, I don't play enough cards. I'm stupid. Missed my 10. And then the jack, the queen, and the king. There's 13 cards in a suit. So of those, though, how many of them have a numerical value on them? 1, 2, 3, 4, 5, 6, 7, 8, 9 have a numerical value. So nine hearts have a number on them. 9 diamonds will have a number. 9 spades will have a number, and 9 clubs will have a number. So when I say what's the probability of picking a number out, picking a card that has a number on it, it would be 36 out of 52. Let me just add those together. Okay, so what would be the probability then of a couple different ways I can write this? Okay, and this is how we refer to as the complement. We can say number with the prime notation. Okay, so I put that a little apostrophe there at the end. I could write the probability, and you see this generally in more advanced courses. You see a little c as that superscript for the word complement. You might even see people rewrite it this way: not a number. Okay, well, that's going to be, okay, well, if it's not a number, then it's either an ace, a jack, a queen, or king. So there's only 4 for that suit. There's 4 then for that one, 4 for that one, and 4 for that one. So I would get 16 out of 52, 16 out of 52, 16 out of 52. These all say the same thing. The question is there a better or easier way of determining that without having to actually look at what those favorable outcomes are? And it's this process right here, that the probability of a complement event is 1 minus the probability of the event. So if I knew that the probability of a number was 36 out of 52, the probability of not a number, which would be the probability of an ace, a jack, a queen, or a king, would be 1 minus the probability of getting a number. And that's 1 minus then 36 over 52. Common denominator would be 52. So 52 over 52 minus 36 over 52. And that gives me 16 over 52, which is exactly what we said over here. Okay. You've probably done just, in everyday life, you see, the probability for rain today was 90%. Okay. I write it this way. Probability of rain was 0.9. So the probability of rain's complement, rain prime, or the probability of rain complement, or the probability of not rain, or if you think about it, you could write it this way: probability of being dry, would be 1 minus the probability of rain, which would be 1 minus 0.9, which gives me 0.1 or 10%. So you've probably seen that concept a lot in your regular everyday life. They're called complement events. If I tell you what's the probability of something happening, then 1 minus that is equal to the probability of that thing not happening. Okay, so this example, you might see a couple like this. As a commuter train runs every 25 minutes, if a commuter arrives at a station at a random time, what is the probability that the commuter will have to wait at least 10 minutes for the train? It says assume that a stop takes very little time. Okay, so sometimes with probabilities and math in general, we have to take assumptions. So a stop is like instantaneously fast. So they stop and they start back up right away. It says draw a line segment to model the situation. The length of the entire segment represents the amount of time between trains. It says a commuter will have to wait at least 10 minutes for the train if the commuter arrives at any time between 0 and 15 minutes. Hopefully that makes sense, okay? Because so this here represents, this 0 to 25 represents the commuter train running every 25 minutes. So one arrives there, and then it disappears, and then it arrives there again, and we repeat that process over and over again. So within, this here, there are no trains at the train station. Okay. Well, if I want to think about when you see this verbiage here of what is the probability that the commuter will have to wait at least 10 minutes? Well, if I think about putting a spot right here, if I show up at the 20-minute mark, am I having to wait at least 10 minutes? No, I'm only have to wait 5 minutes before the train shows up again there at 25. If I show up right there at, let's say, 12 minutes, I'm only going to have to wait, or not, sorry, not 12 minutes, 17 minutes. So let's say that number right there, 17. I'm only going to have to wait 8 minutes. Okay, so I'm not going to have to wait. When I say at least 10, well, 8 is not at least 10. So keep moving my way this way. And if I start there at 15, if I show up at 15, then I'm going to have to wait from 15 to 25 minutes for a train to show up. Okay, so that means that all of this here would be having to wait at least 10 minutes, which means 10 minutes or more. Think about the picture over here. If you show up at that point right there in time, you're going to have to wait 20 minutes. Is that at least 10? Yes, it is. That point right there, I'm going to have to wait 15 minutes. Is that at least 10 minutes? Yes, it is. Any point on this segment right here, any single point on there, when I arrive and compare it to 25, it's going to be at least 10 minutes or more. Okay? So how do we compare those areas? Well, this area here, or not area, length, that length there is the favorable outcomes, and there's 15 of them. This length here is possible outcomes. There's 25 of them. They both have a factor of 5 in them, so it reduces to 3/5. If you want to write that as a decimal, 60%. Okay, so when you, if you're on this schedule, I mentioned earlier that it could be, you call into a call center and you have to wait. Okay, or you go to Happy Days and they've got a average wait of 25 seconds or 25 minutes. When I show up, okay, what's the probability that I have to wait at least 10 minutes? Okay, and this is kind of how we would do this. It would be 60% chance here that you're going to have to wait at least 10 minutes in this particular situation. Just for brevity of the video, I'm going to skip this question here for now. I know I've been making these videos pretty lengthy for you. We can address this maybe in another video, maybe a homework question video. Says when the points of a region represent equally likely outcomes, you can find probabilities by comparing areas. You're going to see probably more questions geared towards this concept, especially on maybe the EOC, than what you would with this concept. And this idea here, we can do this with areas, we can do it with volumes as well. But basically this idea is, I like to think about everything as like a target. And most of you probably think about targets as, I don't know if I might even have a picture of a target here. Yeah. Most of you probably think about targets that way. But really they don't have to be circles. They don't have to be concentric circles like this. Basically what we're looking at is a bunch of different areas that overlap one another. And generally one area is completely surrounded by another area. So here we see this yellow area completely surrounded or encompassed by this area R. So think about this shape here being your dartboard. And I tell you, you're going to throw a dart at this. You're going to close your eyes. You're going to throw a dart at this dartboard. And I want to know, what is the probability that your dart lands in the yellow? Okay. So what you're going to do is you're going to compare the area of the yellow, because that's the favorable outcomes. That's what I want my dart to hit. So that's the area of the yellow in the numerator. And then the area of everywhere that the dart could have hit would have been this region here in blue, which includes the yellow. So that's going to be my denominator. The concept is that we have, and this is kind of where I said we can get a lot more complex if we don't have the condition that I know my dart hit inside this region. If I tell you, if we incorporate the dart for being able to hit out here, it's a whole different ball game and a lot more complex mathematics outside the scope of this class. So what you're going to do in these problems is you're going to look at what is the favorable outcomes. Where do they want me for my dart to hit in this weird looking or bizarre looking target? And then, okay, what is the area of that region? And then what is the area of the entire target? And we're going to divide those. So here we've got a question. So you're going to get into having to utilize and manipulate your area formulas for different shapes. And those area formulas they're going to run the gamut of everything we've talked about so far in this chapter. This first question says a circle is inscribed in a square. So inscribed means that it's tangent there, there, and there. Okay, tangent meaning it touches one time at each of those segments. It says point Q in the square is chosen at random. What is the probability that Q lies in the shaded region? Okay, so we're gonna close our. It says pick point Q. I like to think about it as you're gonna throw a dart, and where that dart lands is point Q. So what is the probability that it would land in one of these yellow regions? Okay, so those are our favorable outcomes. We want it to be in the yellow. Well, how do I find that yellow? These are, this yellow region right here is a very irregular shape. We haven't seen anything like that throughout this course, and we don't have a specific formula for that. But we do have the knowledge that this distance here, and they're telling me this is a square, so that distance right there is 6 centimeters. So then so is that distance, okay, also 6 centimeters. So when I look at the area of the square, that's going to be 6 times 6, or 36 square centimeters. Okay. Now, if I wanted to take and find the area of the yellow, I don't have a specific formula for that other than saying it's going to be the area of the square minus the area of the circle. Well, we already know the square's area is 36 square centimeters. Now the circle, if the side of the square is 6, then all our knowledge about regular polygons being circumscribed around a circle or the circle being inscribed in the polygon tells me, especially for squares, that distance, that radius is 3 if the side length of the square is 6. So that being said, the area of the circle is going to be 9 pi. Because remember, area of a circle is pi r squared. R being 3, so 9, and then times my pi. And that's going to be centimeters squared as well. So when it asks me what is the area of the shaded region, so my favorable outcomes, where do I want my dart to hit? I want it to hit in the yellow, which is this area. So I'm going to have 36 minus 9 pi as my numerator. And then where are all the different possible places it could have hit? Well, it could have hit anywhere. It could have hit here. It could hit there. It could hit there. It could hit there. All of those areas are anything inside the square. So the square's area was 36 square centimeters. So then when you can use Desmos for this, or I know I've been using this calculator here just because of the convenience for me on my iPad. Just bounce back and forth between Desmos or just any browser on this is kind of a pain in the butt. So I'm going to put that in print. That's my numerator. Then we divide by 36. That's my denominator. And I get 0.214. Okay. 6 if you want to keep going. Now the question is, what is the probability that Q lies in the white. Well, what if I want to lie in the white? That could be, and there's a couple different ways you could do this. Think about what is... Oh, I didn't want to do all that. What is the area of the white? Well, the area of the white was 9 pi. So take 9 pi. So that's my favorable outcomes. So I want to land in the white. Divided by the entire square. So 36. And I get that number right there. Okay. Now here's my question. Is there a different way we could have done that? Well, this area right here is laying in the yellow. What if I asked, what is the complement, yellow prime, or yellow complement, or not yellow? Okay. Well, isn't that the same as 1 minus the probability of yellow? So the probability of lying in the white, that probability right there, is the same thing as 1 minus the probability of landing in the yellow. Well, this number here was the yellow. So I'm going to take 1 minus, see if I can copy that number, hit enter, copy that number, and I get that number right there, which if you look at that number, that's the same as that number right there. And I found them 2 different ways. Okay. So that's kind of the idea behind complements and how we can use them to make our calculations a little bit easier in certain applications. The next one says a triangle is inscribed in a square. Point T is in the square, is selected at random. What's the probability that T lies in the shaded region? Okay, so again, what is the area of the square? Now, side lengths are 5. So area of the square would be 5 squared, or 25 square inches. Now, I need to find the area of that region there. Okay. Now, it says that we're inscribed inside the square. I don't know if I completely agree. This is an example cut from the textbook. I don't know if I completely agree with that verbiage there. But basically what I'm going to say is that point right there is halfway, and it really doesn't matter. But if it's halfway in between, I'm going to say, okay, what is that distance right there? That's H. That's my altitude of that triangle. So I'm going to find the area of the white triangle, which would be 1/2 base of 5 times height of 5. So that's going to be 25 over 2. So then what is the probability that we land in the shaded region here? There's a couple different ways you can approach this. Basically, the idea is, okay, so if the white triangle is 25 over 2 and the entire square is 25, then the area of the yellow triangle has got to also be 25 over 2. Or, that ends up being 12.5, if you want to think about it that way. So then what's the probability of landing in a shaded region or the yellow region? Okay, 12.5 over 25, which that reduces to 1/2, 4.5. Not a really interesting question, I think, to show as an example, but let's skip that example right now, the archery question, come down here to these two, and then we'll come back to the archery one. It says a point K in the regular hexagon is chosen at random. What is the probability that K lies in the region that is not shaded? So these little weird, they're not triangles, but they're little weird areas that are white here. Okay, if we were to look at those and kind of enlarge them, they're going to be areas kind of like that. Okay, they really don't have, and we don't have a name for those. Just really bizarre little sections. But what we can do, if I want to find out how much area we have there in white, okay, I have a hexagon. So the area of a hexagon, you remember, that is 1/2 the apothem times the perimeter. Okay. Well, when I'm looking at this, and this is a unique situation, it's a unique problem. When I go down to, if we're looking at just the hexagon, if I draw that little shape right there, remember this is a 60-degree angle. And then I'm going to cut that in half, and I'm going to get a 30-degree angle right there. So that's a 30-degree angle, okay? Now, what we find out is if this distance here is 18, okay? This distance here is 10.4, all right? I'm going to look at this 10.4 because that is a distance specifically to the hexagon. Okay. Now we'll compare that here in a little bit to see if there's anything that we can use or compare to the 18 here. But I'm going to look at this. I need to find my apothem length. Well, if this is 30, okay, remember that cuts, the apothem is going to cut a side length in half. So this is going to be that distance right there. That purple distance is going to be 5.2. Cuts it in half. 5.2. If you remember, across from 30 degrees, that's your inside. This is 60 degrees there. Across from that is your radical 3 side. So my apothem is 5.2 radical 3. Your perimeter then is going to be this 10.4 number multiplied 6 times. So whatever that turns out to be, we'll get a calculator here in a moment, but multiply that out 6 times. So that's going to be the area of my hexagon. Now, the reason they give me this 18 here is because that is telling me that distance right there, which tells me that is 9. So the area of the circle is pi r squared. R squared would be 81 times n pi. So then the area of the white would be the hexagon area minus the circle area. And that's how you find areas of regular shapes. You have to manipulate the areas of known regular shapes that we have formulas for. So I'm going to, and I'll take my calculator and do all this here in a moment, but we'll take 5.2 radical 3 times the 10.4 times 6 value. That's the hexagon. And we'll subtract 81 pi from that. Okay, that's the area of the white. So if I want to know what is the probability of landing in the not shaded region, which would be the white, well, that would be this value here divided by everywhere that I could land, which would be the 1/2, 5.2, radical 3, 10.4 times 6. That's my numerator. So I'm going to type that into my calculator. Be careful here. I'm going to put a parenthesis for my numerator. So then I got 0.5 times my 5.2 radical 3. Then we're going to multiply. So I'm going to multiply that then by the 10.4 times 6. And because it's all multiplication, I'm not too really worried about anything there in terms of order of operations. And minus 81 pi. So that should give me, just trying to look at my parentheses here. Those should all be accurate. I'm not sure what my calculator was. Those first two are not boldened. Oh well. See what happens. And then we're going to divide then by 0.5 times 5.2 radical 3. And then times I just need to make sure that my 10.4 times 6 doesn't end up underneath my radical when I type it in. And that ends up being the area of the white. And you can see it's very small. Okay, if we multiply that by 100, we get 9%, which is it's 1/10 of the overall shape. This problem here, probability of landing in the shaded region. Okay, so we've got some circles here. They don't give us a whole lot of detail. I'm just going to tell you that these circles are tangent to the edge of the square, and they are tangent to one another. So they're only touching there at one point. So you can see these that weird shape right there. We don't have a name for that. Okay, but if I want to find the area of the shaded. Okay, well, that's going to be, I think, the easier thing to do. Probability of shaded would be equal to, now the favorable outcomes would be the 4 circle areas divided by the square area. Because that's all the possible places that if we threw a dart at this, that our dart could land. It could land there, it could land there, it could land there, it could be there. Could be there. Okay. So how do I find the 4 circle areas? Well, these circles I'm going to tell you right now, they're all the same size. So if this is the whole side length is 12 inches, that's got to be 6 inches. And that's the diameter of that circle. So then the radius of that circle would be 3. So the area of one circle would be 3 squared times pi, so I'd get 9 pi. But I have 4 of these things. So 4 areas of the circle would be 4 times 9 pi, or 36 pi. And what's the area of the square? Area square is 12 squared, which ends up being 144. Okay. So that's probability of the shaded. Now, we can do a couple different things here. Well, what's the probability of not shaded? And I've got my notation here on your sheet is kind of messy. Generally, you'll see it this way, I think, in Math Excel. Not shaded or shaded complement. Okay, they might even say probability. Instead of writing out shaded, they might just say S and then complement. All meaning the same thing. Okay, it's just that syntax, that notation. It's not a huge thing to get really concerned about, but we can use it's the complement. What's everything else? Well, we could go 1 minus 36 pi over 144. Okay, or we could do the probability of the non-shaded would be the white area divided by the area of the square. So let's do that. How can I find the area of the white? Well, the area of the white would be the, if you think about just logically, area of white, does it make sense that would be the area of the square minus the area of the 4 circles? Well, the area of the square was 144 minus the 4 circles, which was 36 pi, and then divide that by the area of the square, which we said was 144 again. Okay? So when I look at these, that number right there and that number right there, your neighbor, and you could have done this way, and your neighbor could have done it this way, and you got 2 completely different looking results, but with a little bit of algebra, you'll see that they're the same. And I'll just do this here. I'll do the actual division, so 36 pi. Oh. So I get that number right there, okay? But if I do 144 minus 36 pi and divide that by 144, you see we get the same exact number, okay? So what that tells me is we could do a little bit of, manipulation here. Come over here and do it. 1 minus 36 pi over 144 is the same thing as 144 over 144 minus 36 pi over 144. Well, then we can combine those into one fraction because they have the common denominator, 144 minus 36 pi over 144. And does that match up exactly to that? They do. But my hope is that you guys, especially if we're on the EOC or the ACT, that you logically think this is going to be easier. It's going to be faster to find the area of the shaded and then go 1 minus the area of the shaded, and that will give me the area of the white. Okay, so this one here says an archery target has 5 colored scoring zones formed by concentric circles. The target's diameter is 122 centimeters. The radius of the yellow zone is 12.2 centimeters. The width of each of the other zones is 12.2 centimeters. If an arrow hits the target at a random point, what is the probability that it hits the red zone? Okay. What you need to understand here is that when it says the target's diameter is 122, okay, so we're going out diameter, so 122. So that distance right there is 122. If we cut it in half to get a radius, that would be 61. Okay. It's saying the radius of the yellow zone, so that radius right there is 12.2. And then it says the width of each of the other zones is also 12.2. So this zone right here, when it says width of the other zones, that, better color here, that distance right there is 12.2. That distance is 12.2. That distance is 12.2. and then that distance is 12.2. And if I do that correctly, got 1, so that yellow radius is 12.2, and then I've got another, so a second one, a third one, a fourth one, and a fifth region with the 12.2. Multiply that by 5, it should get 61. So that confirms to me that I've got the right idea here for determining my areas that I'm interested in. Okay, so when it asks me what is the area of the red zone, because I want the probability that I hit in the red, well, let's first look at, so I'm going to take this red, I'm going to outline this, okay, and then I'm going to see if I can pull that back over here. Okay, so if I want to find the area of that red, well, it said the yellow, remember the yellow radius was 12.2, and then the width of the red region right there was also 12.2. So to go from that point there all the way to the edge of that circle would be 12.2 plus another 12.2. So that radius of that circle is 24.4. Okay, so the area of this whole thing right there would be 24.4 squared times pi. Okay, now that is, if I look at my target though, that is not the red section, because the red section is just that right there. So I need to remove the yellow from that. Okay, so I'm going to find the area of the yellow. So remember the area of this. So the yellow one would be that one right there. So can I find that area? Okay, well, that circle had a radius of 12.2. And multiply it by pi. So that's the area of that yellow one. So if I know the area of this one here, which is that area right there, and I know the area of that yellow one, if I subtract those, if I go 24.4 squared pi minus 12.2 squared times pi, that should give me the area of the red. I'm going to give you a word here. It's kind of a donut. Okay, the math word for donut here is an annulus. Okay, so when I look at that red annulus, or ring, that should be this area right here. Okay, so that is going to be my numerator. Okay, well, what's the area of the entire target? Well, we said the entire target had a radius of 61 centimeters. So if I go 61 squared times pi, that's going to be the area of the entire target. And then, like I said, my numerator, it'd be easier just to... My numerator should be that. So, I'm going to go 24.4 squared minus, or sorry, not minus, times pi. And then we'll subtract 12.2 squared times pi. And you get that area there. Okay. I'm going to do, if I hit this button store right here, and then just show you different ways that you can kind of use this calculator, I'll hit X and hit enter. And now every time I hit X, it's going to spit back that number. So I just stored it as that variable. Okay. So I'm going to take then X and we'll divide it by 61 squared pi. So it's going to take the 1402 number and divide it by 61 squared pi and hit enter, and I get 0.12 or 12% chance that when I shoot an arrow, I'm going to hit inside this red annulus. And you could, I mean, it's the same problem over and over again, because they could say, okay, what's the probability of hitting the blue? Okay, well, I'm going to look at the circles that, create that blue annulus, and I'll do the work with those and divide by the entire area of the target. So they could ask the black, they could ask the white, and you might see that in the examples throughout the homework. But that's the idea of geometric probability, and the extent that you're going to be doing those problems. I used to give a problem, and I don't know if it was an instructor created problem to where I would take like a field, like, so you have an aerial view here of like a cornfield, and maybe we've got 2 trees in that cornfield, and we say, well, we're going to estimate that the foliage of those trees are perfect circles. And I could find the radius of that tree. And then I say, okay, well, that's another perfect circle, and I find the radius of that tree. And let's say we have then somebody that parachutes down into this field, and then they're going to land in the field. They're going to land in here, okay? What's the probability that they get hung up in a tree? Well, that would be the probability of getting stuck in a tree would be, okay, the area of the circles. Okay, you have to find the area of that circle and the area of that circle, add them together. And then it'd be divided by the area of the field, which is the rectangle. Okay. The probability of landing on the ground, which would, especially if I've already found that one, could be written this way. The probability of landing on the ground is the probability of not being in a tree, if you think about that logically, or it is the complement of landing in a tree. So if I've already found the probability of landing in a tree, can I just take 1 minus the probability of landing in a tree, and that would give me the probability of landing on the ground. Or vice versa, if I wanted to find the probability of landing on the ground first, I would take the top, it would be the area of the rectangle minus the area of the 2 circles. So that would give me all of this red area. Okay. And then we would divide by the area of the overall rectangle, which when I divide by the area of the overall rectangle, that is including everything inside that rectangle, including the trees. So if I would do that, that would give me the probability of landing on the ground. And then if I had that, then I want to know what is the probability of landing in a tree. It would be 1 minus the probability of landing in the ground. I think a lot of times, like working, and I know this is messy and you don't have any area on your notes to kind of write this example or this logic, but I find a lot of times the hardest part about these questions that people get stuck on is the logic of setting up a custom formula for specific areas.